Hi everyone. Welcome to this evening's stream. Tonight I'm going to do 5 questions on thermodynamics, and well, let's just start. Okay, so thermodynamics, very briefly, is the study of heat. Energy is heat, and the kinetic energy that we studied last semester. We thought last semester that it would disappear under the influence of friction, but no, it actually gets transformed into heat, and this is the continuation of that story. So heat is energy, but it's energy which is so finely diffused through the molecules of a material that you don't see it. You don't see it as motion, although it is there. It's the motion of the subatomic or the atomic particles, the molecular particles. But because you can't see at that level, you can't see that they're moving, and so you don't know that they have all this kinetic energy. That's what heat is. Okay, so this first question is basically making a thermometer based on the thermometer formula, which is an assumption. It's an assumption that there's a linear relationship between how much a material will expand uh, uh, compared to how much the temperature changes. Okay, so for a given temperature change, there's going to be a corresponding change in the length. And that relationship between the change in the length and the change in the temperature, according to this formula, is linear. That's not strictly speaking true. It's only true over small temperature changes, but nonetheless it's good enough for an approximation. Okay, so here I chose some material, acetone, and we're going to make a thermometer based on acetone, and it's accepted that acetone will boil at 56.2 degrees Celsius. Okay, and it freezes at negative 94.8 degrees Celsius. And so we're going to use those two as our reference temperatures, because you need to calibrate a thermometer, you need two temperatures. Okay, and when you're at the negative 94.8, the thermometer, whatever the material is, doesn't matter, it has a length of 35 centimeters. And when it's you take it out of the freezing, you put it into the boiling, it expands to 70 centimeters, and that's it. We can now calibrate this thermometer and make a thermometer that measures in the Celsius scale. Okay, so the first thing is to find alpha. Alpha is the coefficient of linear thermal expansion. Linear because it's just along a line, like a column. Okay, and it's thermal expansion because this thing is expanding thermally. Okay, so find alpha. Well, to do that, we use this formula here. But we have to be careful, because this is delta L, and then there's an L naught here, and there's a delta T, and you go, well, how do I get delta L and delta T information out of there? And so let's do that. Okay, so delta L, whenever you have a delta in physics, what you're basically doing is you're saying the final value minus the initial, or in this case, it's going to be the higher value minus the lower value. Okay, so the higher value is the 70 centimeters, like that. Okay, and the lower value is the 35 centimeters, like that. Okay, and if I subtract the two, you know what, I'm going to change this because I don't want to confuse. I'm sorry, but guys, so let's make it 25 instead of 35, okay? Because then we'll get a little bit more interesting answer, okay? So, the thermometer has a length of 25 at freezing and 70 at boiling, okay? So if I subtract the two now, I'm going to have 45 centimeters, okay? So that's the change in the length over the over the temperature range. Okay, now that's your delta L. What about your delta T? The delta T is going to be the temperature change from freezing to boiling. So that's going to be like the final, or the higher temperature, which is this 56.2 degrees Celsius, minus the lower. But we have to be careful, because this is going to be minus minus, like that. Okay, and so I purposely chose an example, and it's the same in the assignment, and I think I did one like that in the pre-recorded lecture too. I purposely chose an example where the second temperature, the lower temperature, is negative, because you actually have to do a minus minus. Okay, now if that was positive, it would just be a simple subtraction, but no, here we have like a minus minus. Okay, and so this is going to turn out to be 56.2, okay, plus 94.8, okay, and what's that equal to? We will find out in a second using my calculator. All right, it turns out to be exactly 151 degrees Celsius. Okay, so there's the change in temperature. There's your delta T. So now we got the delta L and delta T. Okay, what about the L naught? Now the L naught is actually the lower temperature. It's the reference temperature. We always choose the lower temperature as the reference temperature. Not temperature, I mean length, okay? The reference length. And so that's going to be the 25 centimeters right there, like that, okay? And now we're ready to plug in, okay? You might say, do I have to convert? Okay, and there's two potential conversions that you might do. One is between centimeters and meters, okay, to MKS. And the answer is really, for this equation, you don't have to. You can. It's always safest to do so, but you don't have to. And here's why. Take a look here. See that there is in centimeters, and the L naught is also in centimeters. So if you do both the delta L and the L naught in centimeters, the centimeters would drop out, okay? And so because it's linear on both sides, it has a delta L on one side in centimeters and an L naught on the other side in centimeters. As long as they're both in centimeters, it'll work out. And you'll see that. I'll leave the units in the equation. You'll see that the centimeters will actually cancel out, okay? The other potential transformation is from Celsius to Kelvin. You don't have to do that here because it's a delta temperature. It's a change in temperature. So yeah, it starts off at negative 94.8 Celsius and it ends at 56.2. The difference is 151 Celsius degrees, but it's also 151 Kelvin degrees. Okay, the only difference between the two scales is where do you start to zero. But 1 Celsius degree is exactly the same size as 1 Kelvin degree. So if I say, look, the temperature went out 1 Kelvin degree, or 1 Celsius degree, then it went up 1 Kelvin degree. If I say it goes up 2 Celsius degrees, then it went up 2 Kelvin degrees. It goes up 3 Celsius degrees, then it went up 3 Kelvin degrees. Okay, they're exactly the same size, but what you mean by 0 Celsius is the temperature at which water freezes, and what you mean by 0 Kelvin is absolute zero. Okay, so the zeros are different, but the size of each degree, like the gradation, is exactly the same. So if you say it's a change of 151 Celsius, or you say it's a change of 151 Kelvin, it'd be the same. And you could see that because to change to Kelvin, you would add 273 here, and you would add 273 there, but you're subtracting. And so the 273 that you add to both the temperatures just cancels out. Okay, so there it is. All right. Okay. So I hope that clears up any confusion regarding whether or not you would have to convert here. And so the answer is no, you don't. Okay. And let me just divide both sides of this equation by L naught delta L like this. Sorry, L naught delta T like that. Okay. And now we could just plug in. Okay. And in fact, before I plug in, take a look here. You see how this delta L there is in centimeters and that's in centimeters? They're going to cancel out. Okay, so here delta L we found to be 45 centimeters. Okay, and there's two things in the denominator, both L naught and delta T are in the denominator. Maybe I should put round brackets around it just so you don't get confused, okay? Because if you did this on your calculator and you did divide by L naught but then multiply by T, you'll get the wrong answer. Okay, and so L naught was 25 centimeters like that, and your delta T was 151 like that. All right, now take a look. See that centimeters in the numerator and that centimeters in the denominator? They will cancel. And so, great, we didn't have to convert because the units will just cancel out anyhow. And these are multiplied together like that. Okay, and so let me do that on the calculator very quickly. Turns out to be this number here, and I'll just keep it to 3 significant figures the way we usually do. Okay, it's equal to this. Okay, and you might say, well, what are the units of that? Well, the only surviving unit is degrees in the denominator, so it's per degree Celsius. I know it's kind of a weird unit, but that's what it is. Okay, so it's per degree Celsius, and that's because that's like a fraction growth per degree Celsius. Okay, so that answers part A. All right, and let me see if there's anyone in the chat or any questions. Oh, we got a couple of people viewing. All right. The break is coming up, so I suspect a lot of people will just watch this later, which is fine. Okay. Okay. So there's part A. Part B is if the length is 53 centimeters, what's the temperature. Okay, so now we've already calibrated the thermometer in a sense. So what I mean is we now know how big, if we were to put little markings on the side, we know how big they are, because that's what your alpha is. It tells you how much, what fraction growth you get per degree Celsius. Okay, so all right, fine, let's do that. So this is part A here. Label that. Here's part B, like this. Okay, and for part B, we're still using the same formula, but now what's changed? Well, our delta L, that's what we had before. Let's get rid of that 45. Okay, the initial is still 25. That's like our reference. Okay, so that's going to remain the same throughout. Now, instead of expanding from 25 to 70, like we did when we calibrated it, now we're going to expand from 25 to 53. So the higher number here is 53. Okay, so we start at 25, okay, at acetone freezing, and we expand to 53, this unknown temperature. And what's that going to equal? Oh, all right, let me get that. So it's 53 minus 25 is 28. Okay, so it grew by 28 centimeters. Now, the fact that it's growing means the temperature is going up. How much did it go up? That's the question. Okay, so well, let's continue. We have now delta L. Do we have alpha? Yeah, we have alpha because that's what we calculated in the previous question. Okay, like that. All right. Do we have L naught? Yes, that is our reference length, and that is the shortest length, the length at the freezing, 25 centimeters, like that. And the formula says, okay, now you can calculate delta T. Okay, so let's calculate delta T. Well, that's going to be delta L divided by alpha L naught. Okay, so I'm taking this equation here and dividing both sides by alpha L naught, like that. And what's that going to equal? Well, the delta L, we just said, was 28 centimeters. All right. And alpha, we said, was this number right there. Okay, you know what? I'm going to take the units out because we're just going to always work in these units of centimeters and Celsius. Okay, and what's the other one? L naught. L naught was 25 centimeters, like that. Okay, and what's this equal to? All right, give me a second. Turns out to be 94.1. That is not yet the answer. That is a step along the way to the answer. So here is a typical mistake that's made. I didn't ask for delta T. I asked for the final temperature. The initial temperature is that negative 94.8. That's where it starts. And it increases in temperature by 94.1. So what's your final temperature? Well, your final temperature is, let me write it out explicitly. The way you should be thinking of delta T is not your answer, but it's like your final temperature, T final minus T initial, like that. Okay? And so we know that the delta T, which is what we just calculated, we know that was 91.4. The final T, that's what we want to find. Like what is the final temperature? After it's finished expanding by 53 centimeters, what's the temperature now? So that's our final temperature. And the initial temperature is this, where'd I have it here? This one right here. Okay? So you can see that what this formula gives you, is not the final temperature. It's the change in temperature. And once you have the change in temperature, you know where you started, the initial temperature, you add the change in temperature, and that'll get you to the final temperature. Okay, so that's a mistake that's made, so let's just be careful with that. Okay, and so now we have this. Okay, so if I add the 94.8 to both sides, I'll get that the final temperature is equal to this, the initial temperature, okay, plus how much it increased. Okay, like that. Okay, so just be careful. That's where you started. That's how much the temperature increased above that. And so the final temperature is the sum of the two. And what's that going to be? That is going to be negative 0.07 degrees Celsius, like that. Okay, and that's the answer. Okay, so make sure you understand that, because like on the assignment and on a test, I'm probably I'm probably not going to ask directly for the delta T. What I'll ask is for like a final temperature, okay? And I'll say, okay, so what's this final temperature? As a step to getting that final temperature, you're going to get delta T. And again, remember, delta T is the temperature change above the initial temperature. So you have to take the initial temperature, add the delta T to it, and you'll get the answer that you want. Okay? So there we go. That's question B. And so question B is like more or less how you'd use a thermometer. You'd measure a length with a thermometer, and you translate that into a temperature. Okay, and of course you don't have to do a mathematical calculation on a real thermometer. It's got the numbers right on the side of the thermometer, but someone had to calculate those numbers before they wrote them there on the side of the thermometer, and roughly this is the equation that they used. Okay, so let's go on. The other possibility is, suppose I say, look, I know the temperature in a particular region is 20 degrees Celsius. What's the length of the thermometer going to be? So it's kind of the opposite. In the previous question, I know the length and I get the temperature. Now I know the temperature by some other means. Okay, say another thermometer says 20 degrees Celsius. What do I expect the length of this thermometer to be? Okay, so same approach. Start with this formula here. So this is part C. Okay, start with this formula here. And now what's our delta L? Well, we don't know. Okay, that's what we're going to calculate. Okay, and what's alpha? Well, alpha we found up here, so let me just copy that. There's our alpha. Okay, and what's our L naught? Well, that doesn't change throughout the whole problem. That's our reference length of 25 centimeters. Okay, and what's our delta T? Okay, so the delta T, remember, is the T final minus the T initial. Okay, the final temperature is where you wind up. What did I tell you? You wind up at 20 degrees Celsius. Okay, which incidentally is room temperature. Okay, here in the US we use Fahrenheit, and so usually we say room temperature is 70 degrees Celsius. The equivalent of that in Celsius is 20 degrees Celsius. Okay, so that's our final temperature, 20 degrees Celsius. Okay, like that. And minus the initial, and the initial, you could call it initial, or you could even call it reference. It's the lower one. Okay, it's once again this temperature right here. Okay, that negative 94.8. All right, so what's that going to equal? Okay, so that's going to be equal to 20 plus, because you've got a minus like that, you're going to get plus that like there. Okay, and that is going to equal 104.8 degrees Celsius. Okay, 110, sorry, like that. Okay, all right, so there's our delta T, and now you say, okay, well, I can calculate delta L using this equation there. All right, so for alpha here, I'm going to put in, what am I going to put in for alpha? This number right there. Okay, for L naught, what am I going to put in? I'm going to put in this number here, 25. Okay, and for delta T, what am I going to put in there? I'm going to put in this number right here. Okay, like that. Okay, and multiply all those together, and you get this number here. Okay, that is again not the answer. It is a step along the way to the answer, but it is not the answer. That's not how long the thermometer is going to be. That's how much the thermometer grew above its reference length, and its reference length was 25 centimeters. Okay, so think of this delta L here. You can think of the delta L as your final length, which is what we want. We want to know how long is the thermometer, minus the initial length. And by the way, we call the initial length L naught. Okay, so up here I use the word initial, but we could have just used a little naught subscript. You know, sometimes we use the naught subscript for initial. You remember that from last semester when we had like initial position, we called it X naught. Okay, so L naught is the initial length. Okay, now what do we have here? So here, actually, let me rearrange this so you can see what I'm going to do here. So I'm going to rearrange this, and I'm going to isolate the final L, and that means you're just going to take and add L naught to both sides, so you get L naught plus delta L. Okay, so there's our rearrangement. And this is yet another way to think about it. Okay, what it basically says is, look, your final length that the thermometer is going to be is your initial length plus how much it grew. Okay, the initial length was 25 centimeters. How much did it grow? Well, we just calculated that. It grew by 34 point some decimals there, like that. And what's that equal to? That is equal to, and I'm just going to round off to 3 significant figures. And there it is, to 3 significant figures. Okay, that's what you would actually read off of your thermometer. You would read that it has a length of 59.2. Once again, it started at freezing. Okay, freezing acetone, it started with a length of 25. We heated it up, until we got to 20 degrees Celsius. And I could say, okay, how much did it grow? It grew 34 point, let me just round that off, 34.2 centimeters. That's how much it grew. But it already started at 25, so it grew 34.2 on top of the 25, and now its total length is going to be 59.2 centimeters. Okay, so that's how you solve these problems, all right? And there's not much more to them, and that is roughly how thermometers are calibrated, okay? And I say roughly because it turns out that this only works over a small temperature range. And small could be like maybe 100 degrees Celsius. It depends on the material. But if you start to measure temperatures over large ranges, it turns out that materials don't expand at the same rate all the way along. So if you have two different materials, they won't necessarily agree, even though they're calibrated so that they agree at the two temperatures, the top and the bottom temperature. They won't agree in the middle, and that's because one might start to expand quickly at first and then slow down. The other one might expand slowly at first and then speed up, and so in the middle they don't agree. Think of it like a race, where two people start the race at the same point and they end the race at the same time. Okay, so they're both starting at the same time and they're ending at the same time. That doesn't mean they're going to be at the same place in between. Why? Well, because one runner might get ahead of the other runner, but then they might, like one might be a sprinter. They run fast at first and then they have to slow down, and the other one might be the opposite, runs slow at first and then speeds up. So they both start at the same place and they both end at the same place, but in the middle they're out of sync. Okay, and this really happens, okay, because materials are much more complicated than this linear expansion here, okay, and that's why ideal gases became so important in the study of thermodynamics, because ideal gases really do follow a linear equation over very large temperature ranges, and that's what PV equals nRT is all about. Only here it's not a length, it's a volume. So there's a volume and there's a temperature, and there you go. They've got a linear relationship between the two. Before I move on, let me see if there's any questions in the chat. No, it doesn't look like there's any questions. Okay, so again, a couple people watching. All right, so there we go. There's our generic linear temperature formula. Now we're going to do a PV equals nRT. Now there's many variations on this, and I'm not going to do every possible variation because we'd be here all night. We could just do variations on PV equals nRT all night. I'm going to do one which is a particularly, I wouldn't say hard, but there's a nice trick that makes the problem easy. Let me put it that way, okay? And so I want to show you that trick, all right? And you have one like it in your assignment too. So what do you have here? You have a gas, and its pressure is at 37 torr. And already you're going, whoa, you never even talked about torr up till now. Torr is like the same as a millimeter of mercury, okay? So it's just a measure of pressure. It doesn't even matter. I'm going to show you that you don't even have to worry about converting, okay? Although I think 1 torr is like 133 Pascal. I don't know. You could Google for it. It'll tell you what the conversion is, but we won't need it. We won't need it, okay? And so we have a gas, and it's at a pressure of 37 torr and a volume of 55 cubic centimeters. Okay, and again, you're going to go, do I have to convert that to cubic meters? No, using this method, I'm going to show you, you don't have to convert, okay, which is kind of nice. And 20 degrees Celsius, this you will have to convert, and the reason is, you have to express it in Kelvin. The reason is that temperature there in PV equals nRT must be in an absolute scale. And what an absolute scale means is that the zero in the scale must correspond to absolute zero. Okay, so you can't use Celsius because 0 in Celsius does not correspond to absolute zero. 0 Celsius is what? the temperature at which fresh water freezes. Okay, so water freezes. Okay. By the way, the Fahrenheit scale also uses water, but it used salt water and fresh water as its two reference points. Okay, we don't have to go down that path, but the zeros of these other scales, they're not absolute zero. But the T that you have there in PV equals nRT for this formula to work must be at absolute zero. And the reason is kind of obvious. When you have zero temperature, what's your volume? Zero. Okay. And if you said you had zero volume at 0 degrees Celsius, that means our entire atmosphere would vanish, become vanishingly small. It would freeze out at 0 degrees Celsius, and thank goodness that doesn't happen, because otherwise we won't be able to breathe, when it freezes. No, our atmosphere would actually freeze out. It would actually become a liquid and then a solid at absolute zero, but we don't have to worry about that, because that's like negative 273 degrees Celsius. So that just does those. We don't get those kinds of temperatures on Earth. Okay, so anyhow, so yeah, that 20 degrees we will have to convert to Kelvin. Okay, so let's go back to the problem. We have a gas. It starts off at 37 torr, 55 cubic centimeters, 20 degrees Celsius. We're going to transfer it to another container. Okay, and maybe just to emphasize, I should say we're going to transfer all the gas to another container. And in this new container, the pressure is going to be 55 torrs. It's a bit higher pressure, and it's 75 cubic centimeters, so bigger volume. And what's the temperature in this new container? Okay. Now, one way to do this is you could solve for N. R is the ideal gas constant. We don't have to actually, that number, is given. I would give it to you on a test. So you could solve for N, and then, for the first situation, then substitute it into the second situation. That would work, but here's a much easier way to do it. Okay, we have this equation. Okay, but it applies both to the first situation, which we can put subscript 1 on it, and it also applies to the second situation, where we could put subscript 2 on it. Okay, so you can imagine that you have this equation, but you have it at P1 V1 is equal to N R T1. Okay, and then in our second situation, that is the gas in the second container, it's like P2 V2 is equal to nRT2. Okay, now the first thing you'll notice is I didn't change the R's. That's because it's just this constant, this so-called ideal gas constant. Okay, and it's basically a unit conversion between Pascal meters cubed and Kelvin. Okay, that's all it is. It's just like a conversion factor. If we'd use other units, R would equal 1. Okay, but we're using MKS units, so it's like 8 point, I forget now. Let me just see. I think I have it here somewhere. That's okay. I don't have to look it up, but it's some number. Okay, but we also didn't put a subscript on N. What is N? N is the number of moles of the gas. Now, if you're transferring the whole gas from the first container to the second container, it doesn't matter how many moles there were. It doesn't change. Like you could have had 5 moles in the first container, you get 5 moles in the second container, whatever. Okay. Well, there is a number. I shouldn't say it doesn't matter. There is a particular number, but we don't have to calculate it. There's some number of moles in the first container, and it's the same number of moles in the second container. So you could see here that N remains the same. So what I can do now is I can rearrange this equation here to read NR is equal to P1 V1 divided by T1, like that. What did I do? Well, I just divided both sides by T. Okay, so I have NR on the one side here, NR, and then I have P1 V1 divided by T1. Okay, and I could do the same thing for the second one, like this, only now it's subscript 2. Okay, like that. And notice what we have here. We have NR is equal to something, and then NR is equal to something. Obviously, these two sides, the right-hand side of both of these, have to be equal. And so we have this is equal to this. Okay. The beauty of this equation here, okay, so you can think of this as you could actually think of it as another way of expressing the ideal gas law. The beauty of that equation is that you can plug in the numbers here. You don't have to worry about the units as long as they're consistent. So, if P is measured in torr, here like that, and P1 is measured in torr and P2 is measured in torr, it works out because the torrs on both sides would cancel. If V1 is measured in cubic centimeters and V2 is measured in cubic centimeters, it works out. Okay, so it could be milliliters. As long as V1 and V2 are in the same units, they'll cancel out. Okay, T1 and T2, they have to be in Kelvin. All right, but that's the only one that you have to really worry about converting. Okay, so let's do that conversion first. Okay, so it's T1 I told you was 20 degrees Celsius, which is room temperature, okay? But we need it in Kelvin, so add 273, and that gives you 293 Kelvin, okay? So that is the temperature in Kelvin, okay? And so now we're ready to plug in, and I'll put in the units just to show you that they work out. So for P1, that's 33 torr, okay? For V1, that is 55 cubic centimeters, okay? And for T1, I have 293 Kelvin. That's got to equal, on the other side, 55 torr multiplied by 75 cubic centimeters. Where's my... Oh no, I lost my cursor. All right, there you go. Okay, divided by T2. Okay, we don't know T2, but that's what I'm asking for. What is the temperature in the new container? Okay, and that's what T2 is there, like that. Okay, so take a look. You've got torr on this side, you've got torr on that side. So you could divide both sides by torr. Units work kind of like variables. You could just divide both sides, and so the torr will disappear from here, and the torr will disappear from there. Divide both sides. The cubic centimeters there and the cubic centimeters there, they'll cancel, okay? And you can see that the only surviving unit is Kelvin, so your answer is going to come out in Kelvin, okay? So what's this going to work out to? Well, let me calculate this side. Well, this side is equal to this number here. I'm just going to grab a few extra decimals, okay? Not that we need them, but there they are. And this is going to equal this, okay, divided by T2. All right, and now what? Well, multiply both sides by T2, divide both sides by that 6.94539, like that. And what's this going to equal? There's your answer. Okay, that is going to equal that. Okay, actually let me round it off. Now I'll round off to 3 significant figures. Okay, so the temperature in the new container is 594 Kelvin. Okay, now you might, like my test on multiple choices, you know, you might look and you go, oh, all my answers are in Celsius. Okay, so what do you do now? So what you do to convert to Celsius is, if you subtract 273, that'll give it to you in Celsius, okay? And so what's that going to equal? 321 degrees Celsius, okay? So there it is. So I didn't say whether I wanted the answer in Kelvin or not, but on a test it'd be clear. If I wanted it in Kelvin, there's your answer. If I wanted it in Celsius, there's your answer. Okay, so that's how you solve these types of problems. So, you know, if it's a regular PV equals nRT problem, you just go directly to, like, you know, if I just give you like pressure, volume, and I ask for one of the other quantities, you know, you would just use this. Okay, if you're just using that, by the way, then you do have to use MKS. Okay, and I would give you R on the test. I give you the value of R. Okay, but if you're, say you have a gas and you're like changing some of the parameters on it, like you're changing the pressure, you're changing the volume, or changing the temperature, maybe all three of them are changing, okay, then this is the better way of expressing it right here. Okay, right, provided that you're not adding gas or removing gas, okay, then your ends are not the same, and if your ends are not the same, then you can't say that the left and the right hand side of those two equations are the same. Okay, so there's a PV equals nRT problem. Let's take a look in the chat if there's any questions with that. And there are no questions. Okay, so let's continue. One of the things that I didn't fully derive PV equals nRT. It's not that hard to derive, but I didn't want to expand the lecture too much. But PV equals nRT actually makes the connection between the temperature and the kinetic energy of the particles, okay, that make up the gas, which is really amazing. Okay, so, you know, if I say what's the temperature in the room, that's equivalent to asking what is the average kinetic energy of the particles in the room. Okay, that's kind of mind-blowing. All right, like when you feel that something is cold, equivalently you could say, oh, the molecules in this room are moving kind of slow. Or when it's hot in a room, you could say, oh, the molecules in this room are moving relatively fast. Okay, so it really has to, it really is that simple. And there's the equation that relates the two. The average kinetic energy of the particles in a gas is equal to 3/2 k Boltzmann times T. Okay, the 3/2 comes just purely from geometry, okay, and statistics. Okay, so won't get into the details there, but that's basically a geometrical. The three there is the 3 dimensions of space. Okay, so that's an interesting factor in front there, but it's just 3/2. KB is K Boltzmann. Okay, it's kind of the equivalent of R, which is like the ideal gas constant, okay? But it converts joules to Kelvin, okay, in this equation here, okay? And if we had used different units, K could have equaled 1, but we know we're using these units of joules and Kelvin, the MKS units, and so there's a conversion between joules on the one side and Kelvin there. And so you can see this is a joules per Kelvin. Again, one of these constants that I would just give to you. Okay, and so there you go. This one connects. The first equation connects temperature and kinetic energy, but I didn't ask for the kinetic energy. I asked for how fast on average. Is there a relationship between kinetic energy and speed? Yes, that's the second equation. The kinetic energy is related to the speed because kinetic energy is equal to 1/2 mv squared. Okay, m here has to be the mass of one particle. In this case, they're argon atoms. Okay, and an argon atom, I tell you, is 40 AMU. And you go, well, what's an AMU? Well, 1 AMU is it's like the mass of a proton or a neutron. So 1 AMU turns out to be equal to 1.66 times 10 to the minus 27 kilograms. I might have 6, 7 there. I think it depends on how you round off, but this is close enough. I just got this off of Wikipedia a second ago. Okay, and so let's do the problem. All right. So and the only other thing is that temperature there has to be in Kelvin again. All right. Think about it. When you reach absolute zero, what can you say about the particles? They stop. So when you put T there equals 0, your kinetic energy is 0. Well, if the kinetic energy is 0, then the velocity is 0. Okay. And so that T equals 0 must be absolute 0, not 0 degrees Celsius, which is not absolute 0. Okay. All right. Now we can do this problem. Okay, great. So let's start off. Let's use this first to get the kinetic energy of one particle. It's pretty easy, like just plugging in numbers. But so 3 divided by 2 is 1.5. K Boltzmann is this number right here in MKS units, and the temperature I tell you is 6,000 Kelvin. It's already in MKS units. Okay, so the answer you're going to get is actually a pretty small number, but you would expect that because that's the number of joules for. It's the number of joules for. Why am I getting 0 there? I know why I'm getting 0, because my calculator doesn't, it rounds off too much. Okay, so it's this times 10 to the minus 23. Okay, joules like that. And if you want to write this, like if this were a question, I wouldn't put the number like that. I would move the decimal over. So if I'm going to move the decimal 1, 2, 3, 4 to the right, 4, 2, I moved it 4 to the right, then to the negative 23, the negative 23 there, because I moved it 1, 2, 3, 4 to the right, okay, I would add 4 like that. Okay, and so what's that going to equal? It's going to equal this times 10 to the negative 19. Okay, so there we go. That's the number of joules for one atom of, right there. That's the energy on average for one argon atom at the surface of the sun, 6,000 degrees Kelvin. Okay, now let's convert that to a speed using this equation. Now we're solving for V. Now I like rearranging my equations before plugging in. So I would get that V squared, like this, is going to equal, multiply both sides by 2. So I get 2 kinetic energy like this. All right, so I multiply both sides by 2 to get rid of the half. Divide both sides by m, and that isolates the V squared. Divide by m like that. And so that's my V squared is equal to 2 times the kinetic energy divided by the mass. All right. But now I've got a square there, so take the square root of both sides. And so this is going to equal the square root of 2 times the kinetic energy. Let me put some space in there so it's a little easier to read. Okay, so the velocity is equal to the square root of 2 times the kinetic energy divided by the mass. Okay, so all I did was I just rearranged the kinetic energy is equal to 1/2 mv squared. Okay, isolated v, and I got that. Okay, so it's easier to see, when you plug in the numbers. Okay, so square root of 2, okay, for the kinetic energy, we'll just put in this number right here in MKS. There it is. Okay, divided by m. So now m, you go, oh, what should I put in for m here? So I put a big space in there, because what am I going to put in for m? Because I don't give you m in kilograms, I give them to you in atomic mass units. It's 40 atomic mass units, okay? But each atomic mass unit has a mass of 1.66 times 10 to the minus 27 kilograms. Okay, so what did I do here for m? So this whole thing is m right there. Okay, the 40 is the number of atomic mass units. Each atomic mass unit is 1.66 times 10 to the negative 27 kilograms. So 40 times 1.66 times 10 to the minus 27. That's the mass of one argon atom in kilograms. Okay, so what's this equal to? Well, let me do that on the calculator. All right, well, we'll do it in 2 steps. First, let's do this piece. Okay. All right. And I get this huge number here like that. And now I'm going to take the square root of that whole number. And I get this number here like that. Okay, get rid of those decimals there. There we go. So V is equal to 1,934 units. Well, it's velocity. MKS units are meters per second. Okay. Or if I were to convert this to kilometers per second, because that's kind of an interesting number, and round off a little bit, I get 1.9 kilometers per second. Okay. So that's fast. Okay. 1.9 kilometers, 1.6 kilometers is a mile. So this is a little bit more than a mile every second. Okay, that's how fast these argon atoms are traveling. Okay, which is not surprising, because you've got a hot temperature. Okay, but argon is pretty heavy. All right, if you look at something like oxygen or nitrogen, which is what makes up our atmosphere, and it's O2 and N2. Okay, so it's like 2 oxygens and 2 nitrogens. Okay, they're traveling at roughly 300 to 400 meters per second in our air. Okay, so they're traveling pretty fast too. Like 300 meters per second is 0.3 kilometers per second, but nowhere near as fast as this, which is like getting close to 2 kilometers per second. Okay, so there you go. That's how you do these kinds of problems. You go, well, what are they useful for? Well, conceptually, I think this is probably the most important formula that I've given you in thermodynamics conceptually, okay? And that is because it immediately relates temperature to this average kinetic energy. And it really answers the question, what is heat? It says, look, down there, these atoms and molecules, they're moving. And anything that's moving has kinetic energy. There's the energy. The energy that we lost last semester through friction, and we said became heat. Now we know where it is. It's not that the kinetic energy disappeared. It just became a different kind of kinetic energy. Instead of being the kinetic energy of the whole thing moving, like say a car or whatever, or a roller coaster car, okay, it actually became the kinetic energy of all the little molecules moving around. Okay, and if you add up all that energy, it remains constant. Okay, so energy is conserved if you go right down to the microscopics. Okay, so there it is. There's that problem. Okay, so 2 more problems to go. Actually, 3 more problems to go. Okay, so this one is another one that causes some difficulties, and basically it's a mixing of two liquids, and I have that on the assignment with water and alcohol. But here I just chose two different liquids that were, I just call them liquid A and liquid B, and I made up some numbers. Okay, so I'm going to take 100 grams of liquid A with a specific heat of 3,000 joules per kilogram degree Kelvin. Sorry, degrees Celsius, okay, at 75 degrees Celsius, okay. So I've got this liquid, 100 grams of this liquid A, and it's originally at 75 degrees Celsius, so it's hot. And I'm going to mix it with 150 grams of this liquid B with another specific heat at 10 degrees Celsius. And 10 degrees Celsius is cold. Now what's going to happen? The hot one's going to become cooler, and the cooler one's going to become warmer until they reach the middle, some middle temperature, okay? And I want to know what that final temperature is and how much energy is transferred, okay? And the equation you're going to use is this one, okay? And what does it say? Well, let's go through it piece by piece. This is how much energy is lost by liquid A. This is how much energy is gained by liquid B, and that is therefore the energy transferred, the heat. Q is used as a symbol. It is energy, but it's energy as heat, okay? And so how do you calculate that? Well, if you don't have a phase transition, it's going to be the mass of the material multiplied by the specific heat of the material, multiplied the change of temperature of the material. Now this equation looks a little bit busy, but that's just because I have all these subscripts A in here. But if I just take out the subscripts A for a second, this is the equation that I gave you in during the lecture. M times C times delta T is the energy that either goes into or comes out of a material, okay? Now the reason I put the subscripts A there is because I've got two materials, liquid A and liquid B. Okay, so now we can start plugging in. For material A, we have 100 grams, okay? And I don't really have to convert it, but I'm going to convert it to kilograms, okay, just so that the units look a little nicer, okay, there like that. And material A has a specific heat of 3,000, like that. All right, and the change in temperature is, well, the high temperature, see, delta T is going to be like a high minus a low temperature. The high temperature is going to be 75, and the low temperature is going to be unknown. That's what we're trying to find, the final temperature there, like that, okay? So that one, it's 75 minus T because it's going to start at 75, which is the higher temperature. It's going to drop to a lower temperature T. So 75 minus T is going to be a positive number, okay? That's got to equal, well, same thing for the other side. The mass of B is going to be 150 grams, but converting it to kilograms is going to be 0.15 kilograms. Okay, multiplied by its specific heat, which is this one. All right, 2,200. Okay, and now this one, the delta T there, is going to be the other way around. Why? Because the higher temperature is going to be the final temperature, T, and the initial temperature is the lower one, which is 10. Okay, so this looks a little confusing to students because there I have 75 minus T, and here I have T minus 10. But just remember that the T is going to be less than 75, but bigger than 10. It's going to be something in the middle. I don't know what it is. I didn't solve any of these problems beforehand. But, it could be like 50. And so here it would be like 75 minus 50. And that would be a positive number. And here it would be 50 minus 10. Okay, so that's why for the one that cools down, you subtract T. And for the one that heats up, you subtract from T. Okay, and of course this is all going to equal Q, but we'll do this part after we solve this part. Okay, so now there's a lot of, I wouldn't say a lot of math, but there's some math here. Okay, so next line, what I'm going to do is I'm just going to get rid of the units. Okay, but show you that they work out. There's a kilogram there, and that cancels. Oh, let's do it on this side. Kilogram here, and that cancels a kilogram there. Okay, like that. And there's a kilogram here, and that cancels a kilogram there. Okay, and so there's a degree Celsius there. Okay, and that's going to cancel the degree Celsius there. That's a degree Celsius there, and not cancel, but the answer will come out in degrees Celsius, so we can get rid of that piece. Okay, so the temperatures here will have to be in degrees Celsius, and then there's a joule on this side and a joule on that side. Okay, so the whole equation is in joules, and so your Q is going to come out in joules when we finally calculate that. Okay, so there we go. All right, and just did a little bit of an analysis of the units. 0.1 times 3,000 is 300. So on this side we get this. All right. On the other side we're going to get this, and let me work that out on the calculator. That's 330 times this. Okay. And we'll do the Q later, so I dropped that part. So now we're going to have 300 times 75. 75. That's this number here. Minus, so I'm just distributing 300 times 75, then 300 times negative t is 300 t like that. All right, and then here we're going to have 330 times t, so we got 330 times t minus 330 times 10 is 3,300 like that. Okay, and now what? Well, I'm going to add 3,300 to both sides, so you get this equation here. But when I add 3,300 on this side, that goes away, and over here I'm going to have plus 3,300. Okay, so again I just added 3,300 to both sides, and also I'm going to add 300t to both sides. When I do that, that'll disappear from this side and it'll go to the other side. Whoops, oh, there it worked. It becomes a plus on that side. Okay, so again I added 300t here, and I get 330 plus 300t there. Okay, so now what's this going to equal? That's going to equal this is equal to 300 plus 330 is 630t, and so t is going to equal and I get 41 degrees, 41.0 degrees Celsius. Okay, so there's the answer, at least part of the answer. Okay, and does it make sense? Always ask yourself, does it make sense? So if you look back over here, the hotter fluid starts off at 75. It can't get hotter than 75. When you mix it with a cooler one, it's got to go lower than 75. And so it drops to 41. Okay, so yeah, you went from 75 to 41. That works. And the cooler fluid has to go up. It starts at 10 and goes up to 41. And so yeah, 41 is between 75 and 10. If you had that the final temperature was either greater than 75 or less than 10, you know that you made a mistake. Okay, so there you go. There's the final temperature. And now I asked for the temperature transferred. You can plug in that 41 into this side or that side, and you'll get the same answer. Okay, because we guaranteed that they're equal, and so we'll just use this one to calculate Q like that. Okay, so there's Q, and what is Q? It's the heat transferred. Okay, and it's equal to this, but now we know what T is. T is 41. Okay, and so what's that going to equal? Well, that will equal this number right here. Okay. All right. And what are the units? Joules. I would probably convert that to kilojoules on a test. And so that will equal 10.2 kilojoules. Okay. I'm rounding off here. Okay. So I dropped that decimal right there. Okay. So 10.2 kilojoules. All right. And so that answers that question. Let's see if there's any questions in the chat? Nope. Okay, so there we go. There's question number 4, and that's the mixing of two liquids. Now, I didn't do a latent heat of vaporization or latent heat of fusion. I don't want this to go too long. We've been going nearly an hour already, and thermodynamics, there is a lot to this topic. So, I don't. I know that this week was a little heavier than usual. Okay, so I didn't want to overdo it, but we'll review this again before the test anyhow. Okay, and I could do a latent heat of vaporization, latent heat of fusion there. Okay, so question number 5. It's not really a computational question. I just want to make sure people understand the second law of thermodynamics. So, before the second law, what's the first law say? The first law says energy is always conserved. Okay, always. You say, well, what if there's friction? Yeah, it's still conserved. You just have to add in the heat. Okay, because now we know where that energy went. We know that the energy was converted into heat. So if you include the heat, whatever energy you had before, you have the same amount of energy after. You have a car and it's moving and it comes to a halt and you go, well, the energy disappeared because the car's not moving. No, no, no. Add in the heat and it'll work out. Okay. But that's not all. There's also the second law. And the second law says just because energy is conserved doesn't mean the process will occur. Here's two situations where the process won't occur. Heat only flows from hot to cold. It never flows the other way around. You never get, put a cold thing and a hot thing together, and the colder thing becomes colder, and the hotter thing becomes even hotter. That doesn't happen because that would still conserve energy because whatever energy is lost by the cold is gained by the hot. But you never get into a situation where the hotter thing becomes hotter and the colder thing becomes colder. It's the other way around, like the previous example. The hotter thing will become colder and the colder thing will become hotter until they reach the same temperature. Unless there's something that does work to push the heat from the cold to the hot. Okay, so if you just put a hot and a cold thing together, the hot thing will become cooler and the cooler thing will become hotter, unless you've got a little engine in there and you're doing some work, or not an engine, a compressor. You're doing some work, and then you can force the heat to go from the cold to the hot. Okay, that's what a refrigerator is. Okay, now we did not study refrigerators in depth. Okay, we studied heat engines, but that's what a refrigerator is. And if you and it's kind of hard to reach around the back of a refrigerator to touch the coils that are back there, but and they might be very hot, so you may not want to actually touch them, but just put your hand near them. But they're not that hot. Okay, they're not that hot that they're going to cause a fire or anything like that. Okay, but they're hot. They're warm. Okay, and so what's going on is that the compressor, which you can hear, when your refrigerator runs, it's taking heat, it's making the cooler area cooler, and it's pushing that heat out to the back and making the room warmer. Okay, and so they say, well, isn't that a violation of the second law? No, by themselves, you'll only get heat going from hot to cold. But if you're doing work, then you can force it the other way around. Okay, that's usually called pumping heat. Okay, there's another one. Heat does not become work, okay, unless the heat is trying to flow from a hot to a cold area. So let's just get to this. Heat does not become work, okay? If I've got a box on the ground has a lot of heat in it. That heat isn't just going to magically pop the box up into the air. The opposite would happen. If I drop a box, the energy becomes heat, but the heat cannot, the energy becomes, the work becomes heat, but not the other way around. The heat can't become work, okay? Unless the heat is trying to flow from a hot to a cold area. And that's a situation like if you have, like a hot area, like currents. That's how currents happen in the ocean. The currents are, or the wind. The hot gas is trying to flow to the cold area. Okay, and in doing that, you get wind, and then you can put a little turbine there, and you can get a little bit of the energy out of the wind. And when you do that, you've actually got, you're actually converting a little bit of heat back to work. Okay, so yeah, heat can produce work, but only when it's trying to flow from a hot to a cold area. Okay, so that's it. Those are the two ways of stating the second law of thermodynamics. Stated this way, they're imprecise. They're just qualitative, which is still good because they're a little hard to get your head around. Okay, and so it's imprecise. But the next question, and last question we're going to do tonight, actually makes them precise. Okay, there's the idea of the Carnot efficiency. Okay, so if you have a heat engine running between two temperatures, one temperature is the hot temperature. We'll call it TH for hot. Okay, and in this problem, well, let me read the problem first. Okay, and then I'll explain it as we go through it. So we run a heat engine between 500 Kelvin and 200 Kelvin. If these two temperatures were the same, there'd be no heat flow, because why would it flow? Everything's at the same temperature, and heat only flows from a hot area to a cold area. If everything is the same temperature, there is no hot and cold area. There'd be no flow of heat. There'd be no work. Okay, so there has to be two temperatures in order to get that heat flow, and not only from that heat flow can you get a little bit of work done. Okay, so there's a hot, which is 500 Kelvin. Okay, and there's a cold, which we call T low. Okay, so actually, usually, even though H, like you mean hot, it's like that's a high temperature, and T low is the low temperature. And here, that's 200 Kelvin, like that. Okay, so we have two regions of space, one at a high temperature, 500 Kelvin, another one at a low temperature, 200 Kelvin. If you run a heat engine between that, you can get a maximum efficiency given by what's called the Carnot efficiency. And that's given by the symbol epsilon. So let me grab that symbol so I can cut and paste it in here. There we go. It's usually given the symbol epsilon C, like that, okay? Epsilon meaning efficiency, and C, Carnot. Carnot, there's the name there. It's a French name, so you don't pronounce the final T. That was just the name of the guy who discovered it, okay? Sadi Carnot. He was actually like a lieutenant in Napoleon's army, and he was like all worried about the efficiency of steam engines, like for locomotives, because that was the biggest thing in those days, okay? But instead of calling it Carnot efficiency, we could just as well call it the maximum efficiency. You can't get better than the Carnot efficiency without violating the second law, okay? And so I'm stating that without proof. That can be proven using the ideal gas law, actually. But, I never did prove that in the lectures, okay? So we're just going to take it on faith that the Carnot efficiency is the maximum you're going to get. And it's given by, the Carnot efficiency is given by 1 minus T low divided by T high, like that, okay? That's just a formula for it, okay? And again, that comes out of a proper analysis using the ideal gas law, and you would see that you cannot possibly make an engine that runs between two temperatures, high and low, like that gives you more efficiency than that, okay? And so we can calculate that for our situation. By the way, that formula, T low and T high, have to be in Kelvin. And in this problem, I already gave them to you in Kelvin. If they're not in Kelvin, convert to Kelvin. Okay, so that's going to be that minus T low is 200 divided by 500, like this. And that's going to equal a number which is less than 1. It's 0.6. Okay, like that. By the way, you could also think of that 0.6 as 60% efficiency. That's the maximum efficiency you can build. It's not a technological limit. It's not like you could say, well, if I just did this in a more clever way, maybe I can get better than 60%. No, it's actually a law of thermodynamics, okay? Ultimately a statistical law. You simply cannot get better than 60% efficiency, okay? By the way, what if the two temperatures were the same? So a little bit of an aside now. This is not part of the problem, but just an aside. Suppose that T low was 200 and T high were both 200, so the temperatures are both the same. Well, then you're going to get 200 divided by 200 is 1, so 1 minus 1, which is 0, and there you go. In a region where all the temperature is the same, the best you could do is 0% efficiency, which is no efficiency at all, okay? So you could see that the second law is actually built into this. Okay, the further apart TL and TH are, the more efficiency you can get. Okay, great. So in our particular situation between 500 and 200 Kelvin, the best you could do is 60%. Now, what does that 60% mean? The true efficiency, the actual efficiency, which is just given the symbol epsilon like that, that's going to equal the amount of work done divided by the energy, the heat absorbed from the high energy. Okay, that's just what you mean. You absorb so much energy, so much heat from the hot, and so much of it becomes work. Okay, and the more work you get for the, like if like 100%, suppose like, in our problem here, we absorb 150 joules. Okay, suppose that 150 joules were created. Now this is wrong, but let's just suppose that 150 joules of heat is absorbed and 150 joules of work is done. Well, 150 divided by 150 is 1, which would be 100% efficiency. Okay, so if all the heat that's absorbed becomes work, then you get 100% efficiency. But that can't happen. In fact, here's the rule. Whatever the true efficiency is, it has to be less than the Carnot efficiency. Okay? All engines always run at less than the Carnot efficiency. You can get really close to the Carnot efficiency, but you can't go over the Carnot efficiency. So the best you can ever do, and again, it's not a technological thing. It's not like you can come up with a more clever engine. You simply, it will not, it's simply no engine can run at more than 60% with those two temperatures. Okay, and so over here, using just this piece of it right there, we could say, okay, the Carnot efficiency we found to be 0.6, okay, 60%. The amount of heat that you absorb from the high, that's 150 kilojoules, sorry. There's 150 kilojoules, like that, okay? And so now you've got this equation here, and multiply both sides by the 150, and you're going to get that the work is less than 150 times 6. I'll actually do it this way, like that. Put this on the other side. Okay, there you go. Okay, so the best you're going to do is out of that 150 kilojoules that you absorb, 60% will become work. Okay, that's the best you can do. And so what's that going to equal? That will equal 90 joules. 90 kilojoules. I keep saying joules, but it's kilojoules. Okay, kilojoules, like that. Okay, so how much work is done? Well, I can't exactly tell you. Let me just take out the middle piece in here. I can't exactly tell you how much is done, but the maximum that could be done is 90 joules. That's as best you could do. Okay, you use every technological skill you have, and the most you're going to get is you absorb 150, and 90 of them, of those kilojoules, becomes work. What about the rest? Well, how much is the rest? The rest is lost. Okay, and that's like what you could call the Q low. That's how much is lost to the low temperature. Okay, well, if 150 was absorbed and you converted 90 of it to work, how much is left over? 60 kilojoules. Okay, and so this is the, right here, this is the max work, and this here, this is the minimum lost. Okay, so you absorb 150. The maximum amount of work you can do is 90 kilojoules, and the minimum you would lose would be 60 kilojoules to the cold. Okay, so you can see that you're losing some of that heat. Why? Because the work that's being done is only being done if there's a flow from hot to cold. Well, you can't cut off that flow completely, because if you cut off that flow completely, then you don't have a flow from hot to cold. Okay, all right. So there always has to be some of the heat that flows into the cold area in order for there to be a flow from the hot to the cold. And you can siphon off some of that energy as it's flowing from hot to cold. You can siphon off some of that energy to do work. And you say, well, how much can you siphon off? At most, you can siphon off the Carnot efficiency. 1 minus TL minus over divided by TH. Okay, so there you go. There's the last question. Okay, on the second law of thermodynamics. Let me see if there's any questions in the chat. Well, a couple of you survived right to the end. So let me just ask any questions. If not, we're done. Okay. I'll just wait a second here. And let me just say, I try to make my topics as uniform as possible in terms of the amount of work per week. But I think you could see that thermodynamics has more to it than some of the other topics. And even though I went like for an hour and 8 minutes during this live stream, I still didn't do all the possible problems that we could. But all right. All right, I'm not getting any questions, so I'm just going to say good night to everyone, and end the stream. All right. Good night, everyone.